Okay, I think we're going to go ahead and get started now. Hi, I'm Avnish, and today I'm going to be talking to you about production reinforcement learning and the challenges of doing real-world RL. And so who am I? I am a machine learning engineer working on RL and on our production reinforcement learning library, RLlib, at any scale. Before this, I was a graduate student at USC, where I studied computer science and robotics, and I was doing reinforcement learning for robotic manipulation. And also, during my research, I was an open source software maintainer of some RL and robotic research libraries. And who are we? Any scale, we are the original creators of Ray. We make a unified framework to develop and deploy and manage scalable AI Python applications with Ray. And why do we do it? It's because scaling is a necessity, scaling is hard, and making distributed computing easy and simple for everyone is our mission. So to give you a little bit of an overview of the talk, so I'm going to start by prefacing and saying that this talk is oriented towards people who are maybe lightly ML practitioners or data scientists, but you definitely don't need an RL background to understand anything that I'm saying. So also on the flip side, people who have intermediate to expert backgrounds in RL, you probably won't find too much interesting material in this talk. Okay, so first we'll be talking about what is reinforcement learning at a higher level, and then we'll talk about some industrial use cases that we see with our partners, starting in the video games industry with our partner Riot Games, and then moving to industrial process optimization. We'll talk a little bit about what our friends at Dow Chemicals, Adam Calloway, hi, I see you in the crowd, are doing, and then finally we'll move on to session-based recommendation systems, which personally I think is the most exciting application of RL. And then after that, I'll segue into the challenges of doing real-world reinforcement learning that we see some of our users face. So for example, how do I actually describe my real-world business problem as a reinforcement learning problem? How do I leverage real-world data that I can use to represent my problem? And then finally, how do I serve and deploy train models, train policies? And finally, where does RLlib fit in to help you solve these problems? So reinforcement learning is a paradigm of active learning where we seek to make an agent that optimally makes some sequential decisions. And we're seeking to learn an agent that expresses some intended behaviors. And we're going to guide these behaviors via this concept that we call reward. Now, there are two ways that agents in the paradigm of reinforcement learning can use reward. The first is they can choose to exploit actions in their world that they believe will give them the most amount of reward. And the second is they can choose to explore new actions potentially that may give them more reward than the current most optimal action that they know of, and then they can update their belief over what the most optimal action is. So that was pretty vague. Maybe I'll give you an example of this. I'll motivate it with an analogy. Say that I'm in San Francisco, and it's my job, it's my mission to go and find the best burger joint to be eating the best burger at every single time of dinner. And so I have this belief in my head that Super Duper Burgers is like the best place right now to eat a burger. But then maybe in the future I might decide to explore new burger joints and then update my belief over what is the best burger joint if I find something that's better than Super Duper. And I'll keep doing that for as long as I act. And now I'll express the other goal of reinforcement learning agents, which is to say that the goal of agents is to maximize the total sum of rewards that they experience while they're interacting in their world. And so maybe if I were to use another analogy to motivate this, say that we have an environment where we have a mouse inside of a house. And the mouse's goal is to eat the maximum amount of cheese inside of this house as possible. And there's a little bit of cheese stuck underneath the couch, but the most amount of cheese inside of this house is inside the kitchen. However, there's now a cat inside of this house that I'm trying to avoid because the cat's going to kill me if I come into contact with it. Well, if I were a risk-averse mouse, I would potentially do behaviors like just finding the cheese underneath the couch because that's a safe thing to do. However, if I were a mouse that was taught via reinforcement learning, I would explore and find strategies that would allow me to get the most amount of cheese inside of the kitchen. And I won't be able to get the max cheese if I were to avoid the cat. I need to explore. And so now, taking this mouse and house analogy and moving over to applications in the gaming industry, one of our customers, Riot Games, they make player versus player games in which humans compete against each other, like over the same objectives. This is, I think, an example from their game Teamfight Tactics. And so they make these bots for two reasons. One is to play against human players. And the other is they have this necessity for bots because they have to do QA testing in their games. And QA testing is typically done by humans, and it's very difficult to parallelize and optimize in such a way that it can be done in a time-efficient manner. So Riot then goes ahead and they make bots that are hand-designed. Somebody will go in and express potential behaviors that the bot should express. However, the behaviors are limited in ingredient fashion. And so they can set higher level objectives for their bots via reinforcement learning, via reward. They can say, hey, if you're an agent who's playing the game, you get a reward at the end of playing the game of 1 if you win the game. And you get a reward of 0 if you lose the game. And then using reinforcement learning algorithms, they can train these bots in such a way that they learn long-term strategies that are human-like. And maybe if they're doing QA, it can potentially exploit behaviors in the game that were unintended. And now, segueing to something that doesn't look similar at all, but is, I'm going to be talking at a high level, an approximation, rather, about like what one of our customers in the industry, sorry, not customers, partners, Dow Chemicals does. They have a need to optimize a production process for chemicals inside of their chemical reactors. And you could think of their production process as being made up of multiple production cycles, where after each stage in the production cycle, they have byproducts which either they need to get rid of, they need to store, and they can potentially use these byproducts downstream in their production process to reduce their costs further on. And so their overall goal is to minimize the amount of waste that they make, but maximize the profits that they're making. So if they were to take a greedy approach here, and then to locally optimize on the amount of waste that they're creating and locally optimize to maximize the profits that they're making after each step in the cycle, well, reinforcement learning might take a different approach here. It might actually produce more byproducts at one point in the middle of the cycle, which may end up looking like it costs more overall. However, if they were to use those byproducts downstream, they're actually going to globally minimize the waste and globally maximize their profits. And then finally, I'll talk about recommendation systems. I'll start by talking about like, what a standard recommendation system looks like. So say that like, you're on a service like Facebook, okay? And on Facebook, very naively, if we're recommending content to you, we might take in some data about your geolocation and some data about your age and maybe a couple of pages that you've liked, and then finally we'll combine that with some data over what is like very relevant and current content that you might like. And so we can take this information and feed it into a model, and out can come point-wise recommendations that are in some ranked fashion. However, the thing that's being missed here is that customers are constantly interacting with the recommendations that are given to them on a platform in the form of a session. And so we could almost think about this recommender system as a sequential decision-making agent, which has to react to how the user responds to the recommendations that are given to them. And so in that sense, we could take the session-based data and we could use that to infer user satisfaction and set higher level objectives for a recommendation agent that says you get a reward of 1 if your user is satisfied with the content that is given to them, and you get a reward of 0 if the user is satisfied with the content that is not satisfied with the content that is given to them. And so we could take reinforcement learning and combine it, say, with other key performance indicators that you would otherwise use in your recommendation system, and use that to overall maximize the user satisfaction. Now I'll pivot here, and I'll talk a little bit about the challenges that we see in real-world reinforcement learning that some of our customers face. And so starting with the most basic one, I think often people get very excited about reinforcement learning, but they have difficult formulating their problem. So I'll start by just going through the problem formulation with you guys for this simple example where there is a point mass inside of a maze, and the point mass's goal is to get to the center of that maze. So if we're designing this environment, there's three things that we need to specify. We need to specify three quantities that are called state, action, and reward. So the state of our point mass we could think of in this maze as being some x, y position. And the actions that it can take, in this case, it can move up, and it can move down, and it can move left, and it can move right. And then we have to score it on how well it's doing at its task. And so a very naive reward that we can give it, a naive score that we can give it, is we can say the reward is the distance to get to the center of the maze. Now, there are some things that people, when they go to implement their own problem, run into. But I'll use like this example again to try to motivate that. So for example, it's possible that you're not able to observe all of the quantities that are necessary in order to act optimally, so you'll have an incomplete state space. We call this partial observability. So for example, over here, it's entirely possible that with your point mass, when you translate this up to your real-world problem, you actually only have access to the x position of your point mass, but you don't have access to the y position. And then you'll end up having to still act optimally based off the reward signal that you're given. Sometimes you can succeed, but as you can imagine, this is a pretty difficult challenge to overcome. Now, the next thing is that you can have like very large spaces of states and actions that you need to take, and not too many optimal sequential decision trajectories that you can actually end up taking. And so if we were to think for a second about the way that we actually represent agents in real life, in the context of RLlib, we represent them as neural networks. Well, neural networks are nothing more than vehicles for compression of optimal behaviors. And so if you have these like very large state and action spaces, then it may be difficult to properly compress what is the most optimal behavior to carry out. And then finally, when it comes to reward, well, tuning a reward function is often a lot like tuning a loss function. It has to be smooth, it has to be differentiable. You don't want any sharp edges in it. And in the case of neural networks, you don't really want them to be ranging over very large quantities, because this can lead to quite a few instabilities. And so that's another consideration you have to make. And then also, a lot of people's tasks take on a sequential, sort of a sequential view, which means like first I have to do task A, and then I have to do task B, and then I have to do task C. But rewards are scalar, and so it's not very easy to go about like actually writing these reward functions. And then furthermore, there comes a time, like, for a lot of customers who have to design their agents in such a way that there are some constraints coming from external factors that if the agent is not to follow, they would not be able to act safely. And so a difficulty that we run into here is that policies and agents that are represented by neural networks by nature can't capture these constraints. So for example, if we were to look at this image, if we were to look at this image on the screen right now, it's like you could think of this as a self-driving car environment or world. And there's a car that's about a T-bone. And so naively, if we were to implement no constraints whatsoever, well, it's completely within the possibilities for this car over here that we're controlling to hit the gas pedal and then to actually run right into the car, which is like not very safe. And so we need tools such that we're able to apply constraints. And then finally, there's a good chance you have a lot of real-world data that you can use and leverage to represent your real-world learning problem. You can definitely use it to design and run your simulators, but then there's problems involved over there where your simulator might not be fully expressive of what conditions are in the real world. We call this the sim to real gap. And so Alternatively, you could bootstrap from the petabytes or terabytes or gigabytes of experiences that you have. We call this offline reinforcement learning. And another nice thing about doing offline reinforcement learning is that it looks a lot like supervised learning in such a way that it's very friendly to people who are practitioners of deep learning. And then finally, we have a need to evaluate the models, the agents that we have trained. And in doing so, we might have simulators that we can use to evaluate our trained agents. However, we might also not have simulation at all. And so in the real world, a lot of people will do methods of counterfactual evaluation when they're deploying like a generic model into the real world. One that most of you are probably commonly knowing of is A/B testing. However, in reinforcement learning, we have additional methods of counterfactual policy evaluation that we can use. I have the math up here for this importance sampling estimator, which we don't really have to get into the math of it. Some of you might understand it, and you can definitely ask me questions after this presentation about it if you'd like. And then finally, once we have trained models, once we've trained policies and agents, we need a good strategy for deploying these new models. And so what we've seen with companies who have been able to successfully get to this stage is that often the metrics for deploying a new model are entirely based on heuristics that are very specific to their domain. That, and also they need infrastructure to serve their models in such a way that they can serve the needs that they have. And so all of this is to say that like ideas are easy, but execution is everything. And so RLlib really is, RLlib, the tool that we make at any scale, really is going to be your best bet when it comes to helping you solve your challenges. And so starting with the slide where I talked to you about problem formulation, there's no one easy way to do problem formulation. And so one thing that we found that is really nice is that you can come to our open source Discuss community and our open source Raise Slack community, and you can ask us questions about how it is that you should frame your problem. You can use the community as a whole to help you define your RL problem. It's not just us. There's quite a few people on there who are responding too. I took this screenshot up on the screen here like maybe 2 weeks ago, and there was like 15 new posts that day. And then furthermore, you'll need utilities that allow you to apply those real-world constraints so that your agents can act safely. There's a lot of literature about things that it is that you can try, but one thing that's nice about RLlib is that we've implemented a lot of the standard utilities that you can use. And so up here on the screen, I have snippets of the code that you would use so that you can implement your own action masking model, which would be useful for adding additional safety constraints, and also code for dealing with parametric action utilities, which is especially useful when you're dealing with very large action spaces, which would otherwise be very difficult to learn to. And then finally, I have some side-by-side code here. Sorry, not finally, but I have some side-by-side code here showing how we can leverage real-world data in RLlib. On the left side, I show you what it looks like to just pass your own external simulator to RLlib. On the right side, I show you what it's like to pass a file that has the experiences which you're trying to imitate or mimic or bootstrap your policy from. And as you can see, it's the difference of 3 lines of code. And then finally, similarly for running evaluations in RLlib, on the left side, I show you the code for running your evaluations in a simulator. The code on the left side is actually implicitly already there. I've just put it in for the sake of comparison. But on the right side, I show you how you can load your own data set for evaluation and then express different methods of counterfactual policy evaluation. We've implemented 4 functions here so far: importance sampling, weighted importance sampling, doubly robust method, future importance. But it's very easy to import one of these, extend them, and then pass it on your own. So if there's one that you haven't found, you can definitely implement it yourself. And then finally, you've trained your policies. You need a way to serve them. It's very easy to serve them via reserve. RLlib models directly are servable like very easily. inside RayServe. And so I've shown some like snippet code over here of how it is that you can serve trained models. As you can see, it's also, again, 10 lines. And then finally, going back to what I was saying before about ideas are easy and execution is everything, really when you're going to do real-world reinforcement learning, the likelihood is that you're going to have to try out many different ideas. And so RLlib integrates very well with the existing Ray libraries. It's very easy to do distributed hyperparameter tuning, very easy to do distributed training if your models require like data ingestion that doesn't fit onto a single GPU, distributed data ingestion for people who have data sets that aren't going to be able to fit on one machine in memory. I just showed you serving. And then also via RayTune, we provide very easy methods for doing result management. And then finally, I think this is a point that we haven't really mentioned so much, especially when talking about RayAir, but is definitely like a very big point for people who have tried to onboard onto our products. Is that frequently when they try to onboard and build on top of other ML products to build their ML platforms, they face this migration fatigue. However, our customers have said to us very often that they don't get migration fatigue when they work with us, because integrating with any of your existing platforms is as simple as just writing Python inside of a Ray actor so that you can do the communication between Ray libraries and your own code. So that's all that I have for my presentation. These are pictures of everybody who's working on RLlib today. Thank you so much. OK, yeah, so does anybody have questions, by the way? Thomas is going to walk around and try to pass the mic off to you if you have questions. I'm also available for questions later on the side if you don't want to ask questions in this big room. OK, cool. Oh, yeah, sure, go ahead. How often do I see people using action masking for safety? I think I can't tell you specifically about how our customers use it, but you can see that like if you go in like to the GitHub and you just search up action masking in the Ray repo, people do definitely still try that idea out and use it. Yeah. I think like a general thread here, like when you're doing actual like applying ML in the real world, is that the ideas that you have to try out often just have to be extremely simple. Yeah, and so action masking might not work perfectly, but it definitely is one of those things where you can use to like apply your own safety constraints. Yeah.
Thanks for the talk. So my question is, if I want to use LSTM or like a transformer policy, RNN policy, how easy to like integrate with RLlib currently?
Yeah, that's a good question. So I'm going to go back like a slide or two. OK, so over here one second. Can you guys let me put the slides back up on here? Thanks, yeah. OK, so we have this configuration dictionary over here where you can provide your own models. Sorry, one second. Yeah, where you can provide your own models, OK? And over here, that's where you would do that. At the moment, we do provide LSTM and transformer architectures that you can just import that directly work very well with the RLlib interface. And this quarter, we have it planned so that you can pass your own, like, say if you use PyTorch, you can pass like directly your own NN modules to this instead of having to use the RLlib interface. We're thinking that's going to be a lot easier for people. Yeah.
And to follow on, so what's the biggest change after 2.0, Ray 2.0, any or future works?
Oh, what is the biggest change after 2.0? OK, so after 2.0, we've actually pretty much rewritten RLlib, like we've rewritten most of RLlib actually. So far in our 2.0 changes, we've changed the way that you can debug and implement your own algorithm training loop. We've changed the way that you implement your own policies so that you can easily checkpoint and uncheckpoint them, or you can change the way in which like the inputs go into that policy so that you can serve it very easily. And then we have changes planned for this quarter. So one such change is like we're going to be offering a way for you to do distributed training, but of your policies, but in such a way that, say you're doing distributed training on GPU, all your GPUs don't have to sit on one device. You can actually use GPUs spread across like any number of machines, and we're able to do that by utilizing like the powers that exist within Ray Air today. And then another one is which I discussed earlier, is like we're going to be simplifying the model API so that you can easily pass your own models. Okay, can you give the mic to Adam? Yeah.
Yeah, quick question. Is there plans for the action masking and I guess the parametric models as well to be more like first-class citizens so that I can use your networks, like transformers, LSTMs that you have baked in, but then I also want to do an action mask. I think like for the longest time, it's always been this custom model approach.
Yeah, I hear that. So another thing which like I didn't necessarily mention by name is this connectors API that we have. And so I can't get too much into the details right now, also just because I'm not too experienced with it myself. My other colleagues are. However, you can watch, there's a recording online for a talk that June gave called What's New in Ray 2.0 for RLlib. And he explains pretty in depth on how you can rewrite these action maskings as a connector for your policy. Yeah, so it's like very easily pluggable. The way I would describe it is like if you're familiar with Torch, it's as simple as like adding layers inside of your object. Did that answer your question, Adam? Okay, awesome, cool.
Hi, can you tell a little bit more about what kind of support you have for counterfactual policy evaluation?
Yeah, sure. Where is that? Okay, so today with counterfactual policy evaluation, you can provide your own data set for evaluation, and then we have implemented what we believe to be like the standard counterfactual policy evaluation methods. So importance sampling, the different types of doubly robust methods, and then future importance ranking. Yeah. So we haven't implemented any more right now. However, if there's one that you're looking for that we haven't implemented, go ahead and open up an issue on the GitHub or message us on the RLlib channel on Slack or open a post on discuss.ray.io, and we can go ahead and take a look into that. But honestly, it's like a very easy API to reason about. So you can very quickly inherit from the base class of any of these and then implement your own counterfactual policy method. Oh, sorry, one second. Can you, yeah.
Are the examples on your GitHub repo?
Yes, there are examples on our GitHub repo, yeah. Actually, there's a documentation page on offline reinforcement learning or off-policy learning on discuss.ray.io. I think starting there's like one section on counterfactual policy evaluation. I think starting there would be a good idea. Yeah. Okay, if you have any more questions, reach out to us on the forums. Thank you very much.